Welcome to Nap Labs, where we explore the cosmos slowly, gently, and with wonder. Tonight, we journey to a star system 3,000 light-years from home, where a red giant named Kepler 56 spins in a way no other star of its kind should spin, where planets orbit at impossible angles, and where scientists have discovered something extraordinary, evidence that this star may have consumed one of its own worlds. This is the story of planetary death and cosmic mystery, told softly, told slowly, so that as your eyes grow heavy and your breathing deepens, you might drift among the stars and let the universe carry you to rest. If you're settling in with us tonight, drop a comment below. Let us know where you're watching from and on what time it is where you are. Picture a star, not our sun, though they share similarities. Kepler 56 sits in the constellation Cygnus, the Swan, nearly 3,030 light-years distant. If you could somehow cross that gulf of space, traveling at the speed of light itself, you would journey for more than 3 millennia before arriving. 3,000 years. That is long enough for entire civilizations to rise and fall. Long enough for languages to be born, flourish, and fade into silence. And yet, in cosmic terms, 3,000 light-years is merely a neighbor's yard, a short stroll down a galactic street. The light you would see from Kepler 56, if your eyes were sensitive enough, left that star around the time the first iron-working cultures were developing on Earth, when the Bronze Age was giving way to something harder, something stronger. The photons making their journey across the interstellar void while ancient peoples learned to smelt and forge. By the time that light reaches us now, those civilizations are dust, but the light remembers. Light always remembers the moment of its birth. Kepler 56 is a red giant star. Once, billions of years ago, it was much like our sun, a stable middle-aged star fusing hydrogen in its core, steady and reliable. But stars, like all things, age. When the hydrogen fuel in the core runs out, something beautiful and terrible happens. The core contracts under its own weight, growing hotter and denser, while the outer layers of the star expand, billowing outward like a slow cosmic breath. The star swells, it grows, it becomes a giant. Today, Kepler 56 is 4.2 times larger than our sun. Imagine our sun swelling until it grew more than 4 times wider. If you could place them side by side, Kepler 56 would dwarf our star. And yet, despite being so much larger, this giant star is less dense than air. Its density is just 0.025 grams per cubic centimeter. For comparison, our sun has a density of 1.408 grams per cubic centimeter. Kepler 56 is puffed up, expanded, a balloon of glowing plasma held together by gravity alone. The star glows with a cooler light than our sun. Its surface temperature measures 4,973 Kelvin, about 4,700 degrees Celsius. This is cooler than our sun's surface temperature of 5,700 Kelvin, which is why Kepler 56 appears more orange, more ruddy in color. But do not mistake coolness for weakness. This star is luminous. It shines with 9.6 times the brightness of our sun, radiating its light across the cosmos. And yet, despite all this brightness, despite all this energy pouring out into space, you could not see Kepler 56 with your eyes alone. Kepler 56 is too dim. Only telescopes can glimpse its light, can study its secrets, and can hear the star's heartbeat. Kepler 56 is about 3.9 billion years old. Our Sun, for comparison, is 4.6 billion years old, making this distant red giant about 600 million years younger than our own star. And yet, it has aged faster. It has already exhausted the hydrogen in its core and entered its red giant phase. Our Sun will not reach this phase for another 5 billion years. Why the difference? Mass. Kepler 56 was born with about 1.3 times the mass of the Sun, just 30% more massive. But that small difference makes all the difference in stellar evolution. More massive stars burn hotter and faster. They live shorter lives and age more quickly. Kepler 56, despite being younger, is already further along its evolutionary path. This star has a story written in its oscillations, in the sound waves that travel through its body, bouncing from surface to core and back again. These are not sounds you could hear. Space carries no air to transmit sound waves, but the star vibrates, quakes, rings like a bell struck softly again and again by the churning of plasma within. The surface rises and falls, brightening and dimming in rhythms measured in minutes and hours. These are the star's heartbeat, its breathing, its song. The science of studying stars through their oscillations is called asteroseismology, a word built from Greek roots meaning star and earthquake. Just as geologists study earthquakes to learn about Earth's interior, astronomers study stellar quakes to peer inside stars. The technique is elegant. Different oscillation patterns travel through different parts of a star. Some waves stay near the surface. Others plunge deep into the core. By measuring which frequencies appear and which do not, by analyzing the patterns of brightening and dimming, scientists can map a star's interior structure with astonishing precision. The Kepler Space Telescope, launched by NASA in March of 2009, was designed primarily to find planets around distant stars. It did this by staring at a single patch of sky, monitoring over 196,000 stars continuously, looking for tiny periodic dips in brightness that would indicate a planet crossing in front of its star from our viewpoint. These transits, as they are called, are subtle. A Jupiter-sized planet crossing a Sun-like star causes a brightness drop of about 1%. An Earth-sized planet causes a drop of less than 1/100%. Finding these signals requires extraordinary precision and patience. But the Kepler telescope's extraordinary sensitivity to tiny brightness changes also made it perfect for asteroseismology. The same minute variations that reveal transiting planets also reveal stellar oscillations. And so Kepler became, almost by accident, the greatest asteroseismology instrument ever built. It detected oscillations in thousands of stars, including Kepler 56. The story of Kepler 56 began to unfold in 2012, when scientists studying Kepler data discovered two planets orbiting this distant red giant. They found them using the transit method, watching as the planets passed in front of their star from our perspective, causing tiny but regular dips in the star's brightness. These planets were designated Kepler 56 and Kepler 56c. Kepler 56b, the inner planet, completes one orbit every 10.5 days. It races around its star at breakneck cosmic speed, circling in less time than it takes the Moon to go from new to full and back again. The planet is approximately the size of Neptune. one of the ice giants in our own solar system, though we cannot know for certain if it shares Neptune's composition. It might be a gas giant with no solid surface, just clouds of hydrogen and helium growing thicker and thicker until they grade into liquid, and deeper still until the pressure is so intense that hydrogen becomes a strange metallic form. Kepler 56c, the second planet, orbits every 21.4 days. It is larger, closer to the size of Saturn, that ringed jewel of our own solar system. Both planets orbit very close to their star, closer than Mercury orbits our Sun. Mercury, the innermost planet in our solar system, takes 88 days to complete one orbit. These worlds are far closer to their star than Mercury is to ours. But here is where the story becomes strange. When astronomers used asteroseismology to study Kepler 56 itself, they discovered something unexpected. The oscillation patterns told them about the star's rotation, about which way its spin axis pointed. And what they found was shocking. The star's spin axis was tilted about 45 degrees relative to the orbits of its planets. Imagine the solar system, but twisted. Imagine the sun spinning at a wild angle while the planets continue their stately, orderly procession around the sun's equator. It would be as if someone had grabbed the sun and twisted it, leaving the planets behind. This should not happen. Planets form from a disk of gas and dust that swirls around a young star. This protoplanetary disk is naturally aligned with the star's rotation. The same spin that gave the star its angular momentum gives the disk its orientation. When planets coalesce from this disk, they should orbit in the plane of the star's equator, just as all the major planets in our solar system orbit close to the sun's equatorial plane. And yet, here was a system where the star and its planets were misaligned by 45 degrees. It was the first multi-planet transiting system ever found with such a dramatic misalignment. Single hot Jupiters, those massive planets that orbit extremely close to their stars in just a few days, are often found with tilted orbits. The explanation usually involves migration. The planet formed farther out and then spiraled inward, perhaps through gravitational interactions with other planets or the disk itself. And in the chaos of that migration, its orbit could end up tilted. But Kepler 56 had two planets, and they were orbiting in the same plane as each other, just tilted relative to the star. This raised new questions. What could tilt a star's spin axis after the planets had already formed? Or alternatively, what could tilt the planets' orbits while keeping them aligned with each other, but not with the star? The scientists did not stop with the transit observations. They followed up using one of the 10-meter Keck telescopes atop Mauna Kea in Hawaii, using a technique called radial velocity measurements. This method watches for tiny shifts in the wavelengths of a star's light caused by the star's motion. As a planet orbits, its gravity tugs on the star, causing the star to wobble ever so slightly. When the star moves toward us, its light shifts very slightly toward the blue end of the spectrum. When it moves away, the light shifts toward the red. These shifts are minuscule, but detectable with sensitive spectrographs. The Keck observations confirm the presence of the two known planets, but they also reveal something more, a third gravitational influence, a third tug on the star. Something else was out there, pulling on Kepler 56. The observations had not yet covered a full orbit of this mysterious object, so its properties remained uncertain. It could be a massive planet in a wide orbit, several astronomical units from the star. It could even be a companion star, though that seemed less likely given the dynamics of the system. Eventually, more observations confirmed it. A third planet, designated Kepler 56d. This world is massive, 5.61 times the mass of Jupiter, making it one of the heftiest planets known. It orbits at a distance of 2.16 astronomical units, about twice the distance from the Earth to the Sun, completing one orbit every 2.7 years. Unlike the inner planets, Kepler 56d does not transit. Its orbital plane is inclined such that from our viewpoint, it never passes directly in front of the star. We know it is there only from its gravitational influence, from the way it makes the star wobble. And here was the key to the puzzle. Kepler 56d's orbit is also tilted, inclined relative to both the inner planets and the star. This massive outer planet, pulling gravitationally on the inner system, provides a plausible explanation for the misalignment. The third planet's gravity tugs on the inner planets, pulling on them over millions of years. But the inner two planets, Kepler 56b and c, orbit so close to each other that they are strongly coupled gravitationally. They hold each other in place, maintaining their orbital plane relative to each other even as the third planet pulls on them. The result is that the entire inner planetary system, the plane containing both Kepler 56b and c, can be tilted by the outer planet's influence, but the two inner planets remain coplanar with each other. Meanwhile, the star continues spinning on its original axis, the axis it was born with when it formed from its collapsing cloud of gas billions of years ago. The star's spin does not change easily. It has enormous angular momentum, far too much for the planets to alter significantly over the star's lifetime. And so we have a system where the star spins one way. The inner planets orbit at an angle of 45 degrees to that spin, and the outer planet orbits at yet another angle, pulling on everything. It is a cosmic dance of angles and gravity, of forces balanced over billions of years. But there is something else happening in this system, something darker and more immediate. The two inner planets, Kepler 56, b and c, are doomed. Scientists have calculated their execution times, as one researcher put it, with a touch of dark poetry. Kepler 56 is expanding. As a red giant, the star is slowly growing larger, its outer layers billowing out into space. This expansion will continue for millions of years as the star climbs the red giant branch, as astronomers call this phase of stellar evolution. Currently, the star is 4.2 times the size of the Sun, but it will continue to swell. And as it swells, it will reach out and touch its planets. In approximately 130 million years, Kepler 56 will have expanded enough that Kepler 56b, the innermost planet, will be engulfed. The star's outer atmosphere will reach out and swallow the world. 25 million years later, around 155 million years from now, Kepler 56c will meet the same fate. 130 million years. It sounds like a long time, and by human standards, it is an eternity. 130 million years ago on Earth, the age of dinosaurs was in full swing. Stegosaurus and Allosaurus roamed the planet. Birds were just beginning to evolve from their theropod ancestors. The Atlantic Ocean was still narrow. the continents still slowly drifting apart from their Pangaean configuration. And yet, in cosmic terms, 130 million years is almost nothing. It is less than 3% of the current age of the universe. It is a brief moment. When the end comes for Kepler 56b, it will not be sudden. The process will be gradual, unfolding over thousands or tens of thousands of years. As the star's outer atmosphere reaches the planet's orbit, the planet will begin to plow through increasingly dense gas. This will create drag, friction. The planet will heat up. Its outer atmosphere, if it has one, will be stripped away by the intense stellar wind and radiation. The planet will spiral slowly inward, orbiting closer and closer to the star's core with each passing year. Tidal forces will intensify. The near side of the planet will feel a stronger gravitational pull than the far side, stretching the planet, deforming it. If the planet is a gas giant, its atmosphere will be torn away entirely, boiling off into space. What remains might be a bare core, a rocky or icy heart exposed to the searing radiation of the star. Or the planet might be disrupted entirely, shredded by tides until it becomes a stream of debris spiraling down into the star. Eventually, the planet will merge with the star. The world that once orbited will become part of the star itself. Its atoms mixed into the stellar plasma, its chemical elements distributed throughout the star's outer layers. If there were anyone to watch from a safe distance, they might see a temporary brightening of the star as the planet's material falls in and releases gravitational energy. They might detect changes in the star's spectrum as new elements appear briefly in the atmosphere, and then the planet would be gone, erased, consumed. Kepler 56 ECE will watch this happen, if a planet can be said to watch. It will orbit alone for 25 million years after its sibling's demise, a temporary survivor. But the star will continue to expand. The end for Kepler 56c is just as certain, just delayed. It too will be stripped, tidally stretched, and ultimately consumed. Only Kepler 56d will survive. At 2.16 astronomical units, it orbits far enough from the star that even when Kepler 56 reaches its maximum size as a red giant, the star's outer layers will not reach that far. The massive planet will endure, circling what remains of its star. Eventually, billions of years from now, Kepler 56 will shed its outer layers entirely, puffing them off into space as a planetary nebula, leaving behind a white dwarf, a dense stellar remnant about the size of Earth, but containing most of the star's original mass. Kepler 56d will continue its orbit around this white dwarf, a survivor, a witness to the death of its star and the destruction of its fellow worlds. This is the story that made headlines. A star that will devour its planets, a solar system with an execution date. And yet, there is more to this story. Something even stranger that scientists have only recently begun to understand. In late 2024, a doctoral student named Takato Tokuno at the University of Tokyo was studying Kepler 56's oscillations in detail, applying asteroseismic techniques to map the star's internal structure. And he found something unexpected. He found that Kepler 56's core and outer envelope are spinning at different rates and in different directions. Let me explain what this means. Stars are not solid objects. They are spheres of plasma, ionized gas held together by gravity. Different layers can, in principle, rotate at different rates. The Sun does this to some extent. Its equator rotates faster than its poles, a phenomenon called differential rotation. But what Tokuno found in Kepler 56 was more extreme. The star's core, the dense central region where nuclear fusion occurred for billions of years, is spinning in one direction. The star's outer envelope, the vast bloated layers of gas that make up the red giant's volume, is spinning in a different direction, misaligned from the core by a substantial angle, and the envelope is spinning fast, approximately 10 times faster than is typical for red giant stars. This is strange, very strange. Red giants typically rotate slowly. When a star expands into a red giant, conservation of angular momentum dictates that it should spin more slowly, just as a figure skater spinning with arms extended slows down compared to spinning with arms pulled in. The Sun, when it becomes a red giant billions of years from now, will rotate much more slowly than it does today. And yet, Kepler 56's envelope is spinning rapidly. Something has spun up this star. Something has added angular momentum to the outer layers, speeding up their rotation. And something has caused the core and envelope to become misaligned. Tokuno investigated several possibilities. Could the two inner planets, Kepler 56b and c, have transferred angular momentum to the star through tidal interactions? Tides raised by planets on a star can, over time, transfer angular momentum from the planet's orbit to the star's rotation. This is the same mechanism that has tidally locked the Moon to Earth, and the same mechanism that causes some stars with very close-in planets to rotate faster than expected. But when Tokuno did the calculations, he found that Kepler 56b and c, despite orbiting close to the star, are not close enough or massive enough to have spun up the star so dramatically. Even assuming the most efficient possible tidal interactions, orders of magnitude more efficient than observed in other systems, the two known planets could not account for the star's rapid rotation. There was another possibility, a more dramatic possibility. What if Kepler 56 had once had another planet, a planet that is no longer there? What if the star had already consumed a world? The scenario goes like this. Long ago, perhaps when Kepler 56 was still on the main sequence, still fusing hydrogen in its core, still relatively small and sun-like, there was another planet. This hypothetical planet would have been like a hot Jupiter, a massive gas giant orbiting very close to the star, completing an orbit in just a few days. Hot Jupiters are thought to form farther out in their solar systems and then migrate inward, spiraling down to scorchingly close orbits. This migration can happen through interactions with the protoplanetary disk or through gravitational interactions with other planets. As the star aged and began to expand into a red giant, this hot Jupiter would have found itself in an increasingly precarious position. The star swelled. The planet's orbit, already close, became even closer relative to the star's new size. Tidal forces intensified. The planet began to spiral inward, and then the planet plunged into the star. When a massive planet falls into a star, it does not simply vanish. It carries enormous angular momentum. The planet's orbital motion, its movement around the star, represents a huge amount of rotational energy. When that planet merges with a star, all that angular momentum has to go somewhere. It is transferred to the star's outer layers, spinning them up, making them rotate faster. If this hypothetical planet was on an orbit inclined relative to the star's original spin axis, which is possible if it had migrated inward through chaotic gravitational interactions. Then the angular momentum it delivered would have a different orientation than the star's original spin. The star's deep core, massive and resistant to change, would continue spinning on its original axis, but the outer envelope, less dense and more susceptible to the influence of the infalling planet, would be spun up in a new direction. The result, a star with a rapidly spinning outer envelope misaligned from its more slowly rotating core. Exactly what we observe in Kepler 56. Tokuno's calculations suggest that the consumed planet would have had a mass between 0.5 and 2 Jupiter masses, and it would have orbited with a period between 1 and 6 days before being engulfed. Such a planet would be unremarkable in the catalogue of known exoplanets. Thousands of hot Jupiters have been discovered, but this one, if it existed, left a trace of its existence in the spin structure of its star. This is extraordinary if true. It means that Kepler 56 has already devoured one of its children. The star that will consume Kepler 56 b and c in the future may have already consumed an earlier world. The evidence is circumstantial but compelling. The rapid rotation, the misalignment between core and envelope, the difficulty in explaining these features through any other mechanism. Of course, this is a hypothesis, not yet a confirmed fact. There could be other explanations. Perhaps Kepler 56 was born spinning rapidly, though that does not easily explain the misalignment between core and envelope. Perhaps there are tidal interactions we do not fully understand. Science proceeds by proposing hypotheses and testing them, by gathering more data and refining our models. But the hypothesis of a consumed planet fits the observations remarkably well. Let us pull back from Kepler 56 and consider what this tells us about the cosmos, about the lives of stars and planets, about the nature of solar systems and their evolution. Stars are not eternal. They are born from clouds of gas and dust, collapsing under their own gravity, heating up until nuclear fusion ignites in their cores. They live for millions or billions of years, steadily fusing hydrogen into helium, supported against gravity by the outward pressure of radiation from their cores. And then the fuel runs out, the core contracts, the outer layers expand, the star transforms. In that transformation, the star becomes dangerous to its planets. Worlds that orbited safely for billions of years suddenly find themselves too close. The expanding star reaches out like a slow tide. Close-in planets are engulfed, consumed, destroyed. This is not a rare phenomenon. It is a natural part of stellar evolution, and it will happen to countless planetary systems throughout the galaxy. Our own sun will do this. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin ascending the red giant branch. The sun will swell, growing to perhaps 200 times its current size. At that size, the sun's outer atmosphere will extend beyond the current orbit of Mercury. Mercury will be vaporized, consumed. Venus, too, will likely be engulfed. Earth's fate is less certain. Some models suggest Earth will just barely escape being swallowed, orbiting within the outer fringes of the sun's extended atmosphere. But even if Earth is not literally consumed, it will be rendered uninhabitable. The sun's increased luminosity will boil away Earth's oceans billions of years before the red giant phase even begins. By the time the sun swells into a red giant, Earth will already be a scorched, airless rock, its atmosphere and water long since lost to space. This is the fate of all planetary systems around sun-like stars. The inner worlds are doomed. Only planets orbiting sufficiently far from their star have a chance of survival. In our solar system, Mars might survive, though it will be heavily irradiated. Jupiter and the outer planets will certainly survive, though they will be warmed by the increased radiation from the sun. Europa's ice might melt. Titan's methane lakes might evaporate. These worlds will be transformed, but they will endure. Kepler 56 gives us a preview of this process. It shows us what happens when a star expands and reaches its planets. It shows us that stars can consume their worlds, and that this consumption leaves traces, fingerprints, in the star's rotation and structure. Think about the scales involved. Kepler 56 is 3.9 billion years old. It has existed for nearly as long as the Earth has existed. Civilizations have risen and fallen on Earth. Species have emerged, flourished, and gone extinct. Continents have drifted. Oceans have opened and closed. Mountains have risen and been worn away by wind and rain. And through all of that, Kepler 56 has been shining, steadily fusing hydrogen into helium, warming its planets, a stable beacon in the cosmos. If there had been life on one of Kepler 56's planets, if there had been oceans under thick atmospheres, if chemistry had found a way to create replication and metabolism and evolution, then that life would have had billions of years to develop. The star was stable for billions of years. There was time, there was energy. Perhaps there were worlds with liquid water, with carbon chemistry, with the raw materials for life. But now the star is changing. Life, if it ever existed there, is facing its end. In 130 million years, Kepler 56b will be consumed. Any ecosystems that might have existed on that world or in its atmosphere, if it is a gas giant, will be sterilized. The planet itself will be destroyed. This is not an event that life can survive. There is no way to escape a star's expansion if you are a planet. Of course, we have no evidence that life ever existed in the Kepler 56 system. We do not know if the planets have atmospheres, or what those atmospheres are made of, or whether liquid water ever existed on their surfaces or in their clouds. These are gas giants, worlds more like Jupiter and Neptune than like Earth. And while we cannot rule out exotic forms of life in such environments, they seem less hospitable than rocky planets with solid surfaces and temperate climates. But the principle remains. Stars age, stars change, and when they do, their planets suffer. Any civilization that arose in a system like Kepler 56 would eventually have to confront the reality of its star's evolution. They would need to leave, to migrate outward to more distant worlds, or to other star systems entirely, or perish. This is a challenge that all civilizations orbiting sun-like stars will eventually face, including our own, should humanity and its descendants survive long enough. 5 billion years is a very long time, but it is not infinite. The sun's evolution is as certain as gravity. Our planet's habitability is temporary on cosmic timescales, but 5 billion years is also a very long time by human standards. Complex life has existed on Earth for only about 600 million years. Human civilization is less than 10,000 years old. 5 billion years is 500,000 times longer than recorded human history. There is time. There is so much time. For now, the sun is stable. For now, Earth is warm and wet and alive. For now, we look out at stars like Kepler 56 and see not just the death of worlds, but also the life of stars, the evolution of matter, the grand cycles of the cosmos. When a planet spirals into a star, what exactly happens? The process begins long before the actual merger. As the star expands, the planet finds itself orbiting through an increasingly dense stellar atmosphere. Imagine the planet as a spacecraft re-entering Earth's atmosphere, but on a vastly larger scale. The planet plows through gas. The gas creates drag. Drag dissipates the planet's orbital energy as heat. The planet heats up. If it has an atmosphere, the outermost layers of that atmosphere begin to be stripped away by the stellar wind and by the drag of the star's extended outer layers. Hydrogen and helium, the lightest elements, escape first. Heavier elements may linger longer, but they too will eventually be lost. As the planet loses orbital energy to drag, it spirals inward. Each orbit brings it closer to the star's core. The process accelerates. The closer the planet gets, the denser the stellar atmosphere it encounters, the more drag it experiences, the faster it spirals inward. It is a runaway process. Tidal forces intensify dramatically as the planet approaches the star. The gravitational pull on the near side of the planet becomes much stronger than the pull on the far side. This creates a tidal bulge, stretching the planet along the line connecting it to the star. For a rocky planet, this would create enormous stresses, potentially breaking the planet apart. For a gas giant, the effect is more subtle, but still profound. The planet is deformed, elongated. There is a limit to how close a planet can approach a star before tidal forces overcome the planet's own gravity and tear it apart. This is called the Roche limit, named after the French astronomer Edouard Roche, who calculated it in the 1800s. For a planet orbiting a star, the Roche limit is roughly 2.5 times the star's radius, though the exact value depends on the densities of the star and planet. If the planet reaches the Roche limit before it is fully consumed, it will be disrupted. It will be pulled apart by tides, fragmenting into a stream of debris that continues to orbit the star for a while before finally spiraling in and merging with the stellar atmosphere. This process might be visible from afar as a change in the star's brightness and spectrum. The debris would heat up as it falls in, radiating energy. The star might flare briefly, but if the planet's orbit decays before it reaches the Roche limit, the planet may remain intact all the way down, sinking into the star as a more or less coherent object. In this case, the planet plunges through the star's outer layers like a stone sinking into water, except the water is million-degree plasma, and the stone is a gas giant larger than Earth. Deep within the star, the planet is subjected to temperatures and pressures beyond imagination. The planet's atmosphere, if any remains, is heated to tens of thousands of degrees, hot enough to strip electrons from atoms, hot enough to ionize everything. The planet's core, if it has a solid or liquid core, may survive a bit longer, but even that will eventually melt and vaporize, mixing into the stellar material. The end result is that the planet's atoms become part of the star. The hydrogen and helium from the planet add to the star's already abundant supply of these elements. But planets also contain heavier elements: carbon, nitrogen, oxygen, silicon, iron, and so on. These are elements that were synthesized in previous generations of stars and scattered into space when those stars exploded as supernovae. These elements were incorporated into the planet when it formed, and now they are returned to a star, completing a cycle. The infalling planet's heavier elements will temporarily alter the star's surface composition. Astronomers might detect these changes if they are watching carefully, if they measure the star's spectrum with sufficient precision. The signature would be subtle and would fade over time as the star's convection mixes the new material throughout the outer layers. And the planet's orbital angular momentum, as we discussed, spins up the star's outer layers, leaving a lasting trace of the planet's existence. The planet's orbits are tilted 45 degrees relative to the star's spin, is itself a puzzle worth exploring further. In our own solar system, the planets all orbit close to the plane of the Sun's equator. The Sun's spin axis is tilted only about 7 degrees relative to the planet's orbital plane. This alignment is expected because the Sun and planets formed from the same rotating disk of gas and dust. About 4.6 billion years ago, a cloud of gas and dust in our region of the Milky Way began to collapse under its own gravity. Perhaps it was triggered by the shockwave from a nearby supernova. The cloud was rotating slowly, as most interstellar clouds are, imparted rotation from the turbulent motions of gas in the galaxy. As the cloud collapsed, it spun faster, like a figure skater pulling in their arms. Conservation of angular momentum dictates this. The cloud flattened into a disk with a dense concentration of material at the center. That central concentration became the Sun. The disk around it became the planets. Because everything formed from the same rotating structure, everything ended up orbiting in approximately the same plane, aligned with the Sun's rotation. There are small deviations. Planetary orbits are slightly tilted relative to each other, and the Sun's equator is tilted about 7 degrees relative to the planet's mean orbital plane. But these deviations are minor. The overall system is well aligned. So what happened to Kepler 56? Why are its planets so dramatically misaligned? The presence of the massive outer planet, Kepler 56d, is likely key to the answer. This world has 5.6 times the mass of Jupiter. That is a very massive planet, close to the boundary between planets and brown dwarfs, those objects that are too massive to be considered planets, but not quite massive enough to sustain hydrogen fusion like a true star. Kepler 56d's gravitational influence on the inner system is substantial. Over millions of years, this planet's gravity can change the orientation of the inner planet's orbital plane. This is a subtle effect, requiring sophisticated orbital dynamics calculations to understand fully. But the basic idea is straightforward. A massive outer planet pulls on the inner planets, and over long timescales, this tugging can tilt their orbits. But this raises a question. Why is Kepler 56d's orbit also tilted? If the planets all formed from the same disk, they should all start out in the same plane. What tilted Kepler 56d's orbit? There are a few possibilities. One is that Kepler 56d formed in place, but then had gravitational interactions with other massive objects, perhaps another planet or a passing star, that perturbed its orbit and tilted it. Another possibility is that Kepler 56d did not form where it is now. It might have formed farther out and migrated inward, and during that migration, its orbit was tilted by interactions with the protoplanetary disk or by gravitational scattering from other planets. Or perhaps the missing planet, the hypothetical world that may have been consumed by the star, played a role. If that planet had significant mass and an inclined orbit, its gravitational influence could have affected the other planets' orbits before it was engulfed. When it plunged into the star, the system's dynamics would have changed suddenly, potentially leaving the remaining planets in tilted configurations. Planetary dynamics are complex. Multiple planets interacting gravitationally can produce a rich variety of orbital configurations. Systems can be stable for billions of years and then suddenly become unstable due to resonances or perturbations. Planets can be ejected from their systems or sent plunging into their stars or scattered into distant, eccentric, tilted orbits. The Kepler 56 system may have experienced dramatic dynamical evolution early in its history, settling into its current configuration only after a chaotic phase. Further, into the broader context of exoplanet science, Kepler 56 is just one of thousands of exoplanetary systems discovered over the past 3 decades. The first confirmed exoplanets orbiting Sun-like stars were announced in 1995 when astronomers Michel Mayor and Didier Queloz detected a Jupiter-mass planet orbiting the star 51 Pegasi every 4.2 days. That discovery was revolutionary. It showed that planets exist around other stars, and it showed that those planets can be very different from the ones in our own solar system. 51 Pegasi, B as the planet is called, is a hot Jupiter, a gas giant orbiting extremely close to its star. No planet like this exists in our solar system. Our Jupiter orbits far from the Sun, taking nearly 12 years to complete one orbit. The existence of hot Jupiters was unexpected and challenged theories of planet formation. How could a massive gas giant form so close to its star, where the disk would have been too hot for ice and gas to condense? The answer, astronomers now believe, is that hot Jupiters do not form where we find them. They form farther out, beyond the so-called snow line where water ice can exist, and then migrate inward. This migration can happen through several mechanisms. Early in the system's history, the planet might interact with the protoplanetary disk, the disk of gas from which it formed. Gravitational torques between the planet and the disk can cause the planet to lose orbital angular momentum and spiral inward, a process called Type II migration. Alternatively, if there are multiple massive planets in a system, they can gravitationally scatter each other. One planet might be flung into an eccentric orbit that brings it very close to the star at its closest approach. Tidal forces from the star can then circularize that orbit, leaving the planet in a close circular orbit as a hot Jupiter. In this scenario, other planets might be ejected from the system entirely or sent into distant, eccentric orbits. The Kepler mission and other exoplanet surveys have revealed an astonishing diversity of planetary systems. There are systems with multiple super-Earths, rocky planets more massive than Earth, orbiting close to their stars. There are systems with planets orbiting binary stars, 2 suns instead of 1. There are systems with planets in highly eccentric orbits, plunging close to their stars and then swinging far away. There are planets orbiting dead stars, white dwarfs and neutron stars, survivors of their stars' violent death throes, or second-generation worlds that formed from the debris. And there are systems like Kepler 56, where the architecture reveals a complex history, where misalignments and rapid stellar rotation hint at lost planets and dramatic past events. Each system is a puzzle. Each system tells a story of formation, evolution, migration, and sometimes destruction. By studying these systems, we learn about the processes that shape planets, about the forces that govern their orbits, about the timescales on which solar systems evolve. Technology that allows us to study Kepler 56. The star is 3,000 light-years away. We cannot send a spacecraft there. The fastest human-made object, the Parker Solar Probe, travels at about 192 kilometers per second at its fastest. At that speed, it would take over 4 million years to reach Kepler 56. Even traveling at the speed of light, which is physically impossible for any object with mass, the journey would take 3,000 years. And yet, we can study this star in exquisite detail. We can measure its size, mass, temperature, composition, rotation rate, and internal structure. We can detect planets orbiting it. We can measure those planets' sizes and masses. We can predict when those planets will be consumed by their star, all from a distance of 3,000 light-years, using only the light that reaches us. This is the power of astronomy. It is the power of careful observation, of sensitive instruments, of mathematical analysis, of physical understanding. Light is our messenger. Light carries information encoded in its brightness, its color, its spectrum, its variability. By catching photons that have traveled for millennia across space, by studying those photons with telescopes and spectrographs and computers, we can decode the information they carry and reconstruct the nature of distant worlds. The Kepler Space Telescope, which discovered Kepler 56's planets and measured its oscillations, was a marvel of engineering. It carried a photometer, a light-measuring instrument, with a 95-megapixel camera. It stared at one patch of sky, a region about the size of 2 fists held at arm's length, containing over 196,000 stars. It monitored those stars continuously for 4 years, measuring their brightness every 30 minutes. The precision was extraordinary. Kepler could detect brightness changes as small as 20 parts per million, 1 part in 50,000. This is equivalent to detecting the dimming caused by a single porch light turning off in a city full of lights viewed from space. Such precision was necessary to detect Earth-sized planets transiting sun-like stars, which cause brightness drops of less than 1 part in 10,000. Kepler operated from 29 until 2018, when it finally ran out of fuel. It discovered over 2,700 confirmed exoplanets and identified thousands more candidates awaiting confirmation. It revolutionized our understanding of planetary systems and revealed that planets are common in the galaxy. Nearly every star has planets. There are billions of planets in the Milky Way alone. After Kepler, other missions have continued the search. The Transiting Exoplanet Survey Satellite, TESS, launched in 2018, is surveying the entire sky, looking for transiting planets around the nearest and brightest stars. TESS has found thousands of planet candidates. Ground-based telescopes equipped with spectrographs measure radial velocities, detecting planets through the wobble they induce in their stars. And future missions are planned that will not just detect planets, but study their atmospheres, searching for signs of habitability or even life. The James Webb Space Telescope, launched in 2021, can observe the spectra of transiting exoplanet atmospheres, looking for molecules like water vapor, carbon dioxide, methane, and oxygen. These observations are beginning to reveal the compositions of alien atmospheres, telling us whether these worlds are habitable, whether they have oceans, whether their air is breathable. We live in a golden age of exoplanet science. A generation ago, we did not know if planets existed beyond our solar system. Today, we know of thousands, and we are beginning to characterize them in detail. Stars like Kepler 56 are no longer mysterious points of light, but are becoming understood systems with histories and futures that we can model and predict. Poignancy to the story of Kepler 56, a melancholy beauty in the fate of its planets. These worlds have orbited their star for billions of years, stable and patient, circling endlessly through the vacuum of space. If we could watch at a vastly accelerated speed, time-lapse photography spanning eons, we would see the planets tracing out their orbits like clockwork, year after year, million years after million years. And then the star begins to change. Slowly at first, imperceptibly. The star brightens. Its surface cools slightly, taking on a more orange hue. The star swells, growing larger. The planets continue their orbits, unaware, unfeeling. They are not alive. They cannot know what is coming. But the end is inevitable. The star reaches out. First, Kepler 56. B feels the touch of its star's outer atmosphere, a gentle brushing of rarefied gas. Then more. The drag begins. The planet slows. It spirals inward. The heat intensifies. The planet is stripped. And finally, the merger. The planet that existed for billions of years becomes part of its star, erased from existence as an independent world. This is not tragedy in the human sense. Planets do not suffer. They do not fear or grieve. But there is something profound in the inevitability of it, in the way the universe operates according to laws that are indifferent to the existence of any particular world. Stars evolve because of the physics of nuclear fusion and gravity. Planets are consumed because they happen to orbit too close when their star expands. There is no malice, no intention, just cause and effect playing out across billions of years. And yet, from our human perspective, we can find meaning in these stories. We can see in Kepler 56 a reflection of impermanence, the reality that all things change, that nothing lasts forever. Stars die, planets die, galaxies evolve, and eventually, trillions of years from now, will exhaust their supplies of gas and stop forming new stars. The universe itself will grow cold and dark in the unimaginably distant future as its expansion continues and the remaining stars burn out. But that end is so far away that it might as well be infinite. For now, the universe is young and vibrant. Stars are still forming. Planets are still coalescing. Life, at least on Earth and perhaps elsewhere, is flourishing. There is so much time left, so much yet to happen. Kepler 56 will consume its inner planets in 130 million years. That is a long time from now. Those planets will orbit, undisturbed, for 130 million more years before their end. There is a peace in that, a sense that even doomed worlds have time, have existence, have their place in the cosmos for now. The concept of stellar oscillations more deeply, the technique called asteroseismology that allowed scientists to peer inside Kepler 56 and discover its rapid rotation and misaligned internal structure. Stars are not silent, they ring with sound. Not sound that we can hear, of course, because sound requires a medium and space is a vacuum. But stars vibrate. Their surfaces rise and fall, driven by pressure waves and gravity waves traveling through the stellar interior. These waves are generated by turbulence in the star's convective zone, the outer layers of the star where heat is transported by the churning motion of hot plasma rising and cool plasma sinking. Think of a pot of boiling water, with hot water rising from the bottom and cooler water sinking from the top. Stars have similar convective motions, though on a vastly larger scale and at temperatures of millions of degrees. This convective turbulence generates sound waves, pressure waves that travel through the star. Some of these waves travel inward toward the core. Some travel outward toward the surface. The waves reflect at boundaries where the density or sound speed changes sharply, bouncing back and forth through the star's interior. If the geometry is just right, if the waves traveling in one direction constructively interfere with waves traveling in the opposite direction, a standing wave is set up. The star begins to oscillate in a particular pattern, a mode of vibration, much like a bell ringing at a particular pitch or a guitar string vibrating at a particular frequency. Stars have millions of possible oscillation modes, each corresponding to a different pattern of vibration. Some modes involve the entire star expanding and contracting radially. Others involve the surface moving in complex patterns, with some regions rising while others fall. The frequencies of these modes, the rates at which the star oscillates, depend on the star's internal structure, its density profile, its temperature profile, the composition of different layers, the rotation rate. By observing which modes are present and measuring their frequencies, astronomers can infer the star's internal structure. It is like listening to a bell and, from the pitches of the sounds it makes, determining the bell's shape, size, and the material it is made from. Different bells make different sounds. Different stars have different oscillation patterns. For Sun-like stars on the main sequence, the oscillation periods are typically around 5 minutes. The Sun itself oscillates with periods ranging from about 3 to 15 minutes, with the strongest oscillations around 5 minutes. These are called 5-minute oscillations, and they were first detected in the 1960s. It took years to understand that these oscillations were global modes of the Sun, standing waves resonating through the solar interior. For red giants, the oscillation periods are longer, typically hours or even days. This is because red giants are much larger than main sequence stars. The larger the star, the longer it takes for sound waves to travel through it, and thus the longer the oscillation periods. Kepler 56's oscillations have periods of several hours. By measuring these periods with great precision and by identifying which oscillation modes are present, scientists can map the star's interior structure. They can determine the size of the core, the boundary between the core and the envelope, the rotation rate of different layers, and more. This is how Tokuno discovered that Kepler 56's core and envelope are misaligned. Different oscillation modes sample different parts of the star. Some modes are sensitive to the core's properties. Others are sensitive to the envelope's properties. By comparing the frequencies of these modes, Tokuno could determine that the core and envelope are rotating at different rates and in different directions. affects oscillation frequencies through what is called rotational splitting. If a star is not rotating, then oscillation modes with the same number of nodes but different azimuthal patterns, different orientations around the star's rotation axis, have the same frequency. But if the star is rotating, these modes have slightly different frequencies. The amount of splitting depends on how fast the star is rotating. Moreover, different oscillation modes are affected by rotation in different parts of the star. Modes that penetrate deep into the core are sensitive to the core's rotation rate. Modes that are confined to the envelope are sensitive to the envelope's rotation rate. By measuring the rotational splitting of many different modes, astronomers can construct a rotation profile of the star, showing how fast different layers are rotating. In Kepler 56, the observed rotational splitting patterns indicated that the envelope is rotating rapidly, about 10 times faster than typical red giants. The core is rotating more slowly, and the two are misaligned, with the core's rotation axis tilted relative to the envelope's rotation axis. This kind of detailed information was impossible to obtain before the era of space-based asteroseismology. Ground-based observations are limited by Earth's atmosphere, which distorts starlight and makes it difficult to measure brightness changes with the precision needed for asteroseismology. Space-based telescopes like Kepler, orbiting above the atmosphere, can achieve the necessary precision. The Kepler mission was not designed primarily for asteroseismology. It was designed to find exoplanets, but the data it collected turned out to be ideal for stellar oscillation studies as well. This is a common theme in science. Instruments built for one purpose often end up enabling discoveries in completely different areas. Serendipity plays a role in scientific progress. The Kepler 56 may have consumed a planet is not just based on the star's rapid rotation. It is also supported by theoretical models of how stars and planets interact. These interactions are governed by tides, the same force that causes Earth's oceans to rise and fall in response to the Moon's gravity. Tides arise because gravity weakens with distance. The side of the Earth facing the Moon feels a stronger gravitational pull than the side facing away. This difference in gravitational force stretches the Earth slightly, creating a tidal bulge. The same effect happens between planets and stars, though the scales are much larger. When a planet orbits close to a star, the star raises tides on the planet, and the planet raises tides on the star. These tides dissipate energy through friction, converting orbital energy into heat. Over time, this energy dissipation causes the planet's orbit to decay. The planet spirals inward. How fast this happens depends on several factors: the planet's mass, its orbital distance, the star's size and structure, and the efficiency of tidal dissipation. For planets orbiting very close to their stars, the timescale for orbital decay can be quite short, cosmically speaking, perhaps only millions of years. For planets orbiting farther away, the timescale can be billions of years or longer. Kepler 56's inner two planets, Kepler 56b and c, are currently stable. Their orbits are not decaying rapidly, but that will change as the star continues to expand. As the star grows larger, it will reach closer to the planets. The tidal forces will intensify. The orbital decay will accelerate. The calculations that predict Kepler 56b will be consumed in 130 million years. take into account the expected growth of the star and the strengthening of tidal forces as the star approaches the planet's orbit. These calculations are based on models of stellar evolution, which have been tested and refined over decades using observations of many stars at different evolutionary stages. Of course, there are uncertainties. Stellar evolution models depend on assumptions about the star's composition, the efficiency of convection, the presence of magnetic fields, and other factors. Small changes in these assumptions can lead to differences in the predicted timescales. But the overall picture is clear. The star is expanding, the planets are doomed, and the timescales are on the order of hundreds of millions of years. About what it would be like to observe the consumption of a planet from a safe distance. Imagine you have a telescope powerful enough to resolve Kepler 56's surface, to see details of the star and its planets. You watch for thousands of years, accelerated to see changes that would normally be imperceptible. At first, nothing seems to happen. The planets orbit, the star shines. Year after year, century after century, millennium after millennium, the scene is unchanging. But then, slowly, you notice the star growing larger. It is subtle. You would not see it if you were not watching carefully. But over 10,000 years, the star has visibly swollen. The innermost planet, Kepler 56b, continues its orbit, still far from the star's surface. But the gap is closing. After 100 million years, the star has grown enormous. It has swollen to many times its original size. The planet now orbits within the star's outer atmosphere, plowing through tenuous gas with each orbit. The planet begins to glow more brightly, heated by friction with the stellar atmosphere. It develops a comet-like tail, a stream of gas being stripped from its atmosphere and left behind in its orbit. The planet's orbit is visibly decaying now. Each orbit brings it closer to the star's core. The spiral accelerates. Within a few thousand years, the planet has moved dramatically inward. The star's disk grows larger and larger in the planet's sky, until the planet is skimming just above the visible surface. And then it plunges in, disappearing beneath the glowing photosphere. For a brief time, you might see a bright spot on the star's surface where the planet is releasing gravitational energy as it falls. You might see changes in the star's spectrum as the planet's material mixes into the stellar atmosphere. And then, nothing. The planet is gone. The star shines on, slightly brighter perhaps, slightly altered in composition, but otherwise unchanged. One fewer planet orbits. One world has been erased. This is not a violent event, not an explosion or a collision. It is a gradual merging, a slow absorption. The universe is gentle in its destructions as well as its creations. History of the Kepler 56 system, the full story from birth to the present and onward to the future. About 4 billion years ago, a cloud of gas and dust in this region of the galaxy began to collapse. The cloud was enriched with heavy elements from previous generations of stars, stars that had lived and died and exploded as supernovae, scattering their enriched material into space. The collapsing cloud formed a rotating disk. At the center, the proto-Kepler 56 grew, accumulating mass, heating up. Farther out in the disk, clumps of material began to coalesce, growing through collisions and gravitational attraction. These clumps became planetesimals, small rocky or icy bodies. The planetesimals collided and merged, forming larger bodies. Eventually, some of these bodies grew large enough to gravitationally attract gas from the surrounding disk, forming gas giant planets. Perhaps there were more planets originally than we see today. Perhaps there were 5 or 6 or more worlds, some rocky, some gaseous. They orbited the young star, their orbits gradually clearing lanes in the protoplanetary disk, sweeping up leftover material. The system was not stable. Gravitational interactions between the planets led to a period of dynamical instability. Planets migrated. Orbits became eccentric. Some planets were scattered, perhaps ejected from the system entirely. One planet, a hot Jupiter, migrated inward to a very close orbit. Its presence may have perturbed the orbits of other planets, tilting them, scattering them. Eventually, the system settled into a quasi-stable configuration. Kepler 56b and c orbited close to the star, tilted relative to the star's spin. Kepler 56d orbited farther out, massive and influential, and the hot Jupiter continued its close orbit. For billions of years, the system was stable. The star fused hydrogen in its core. The planets orbited. Perhaps there was weather on these worlds, storms of hydrogen and helium, lightning in the clouds, winds howling at hundreds of kilometers per hour. Perhaps moons orbited some of the planets, small rocky or icy bodies locked in tidal embrace with their giant parents. And then, perhaps a few 100 million years ago, the star began to expand. It exhausted the hydrogen in its core. The core contracted and heated. The outer layers expanded. The star grew larger, and the hot Jupiter, orbiting so close, found itself in danger. The planet spiraled inward. Over tens of thousands of years, it plunged into the star, transferring its angular momentum to the star's envelope, spinning up the outer layers, leaving a trace of its existence. The planet was gone, but Kepler 56's rapid rotation remembers it. Now, the system continues. Kepler 56b and c orbit, oblivious. Kepler 56d orbits farther out, a massive sentinel. The star grows slowly larger, climbing the red giant branch. In 130 million years, Kepler 56b will meet the same fate as the hypothetical hot Jupiter. 25 million years after that, Kepler 56c will follow. Eventually, the star will reach the tip of the red giant branch. It will ignite helium in its core, fusing helium into carbon and oxygen. This helium flash will cause the star to shrink slightly and become less luminous. The star will settle into a new phase, the horizontal branch, where it fuses helium steadily for a while. But this phase is shorter-lived than the main sequence. After a few 100 million years, the helium in the core will be exhausted. The star will expand again, becoming an even larger red giant, ascending what is called the asymptotic giant branch. The star will pulse and vary, shedding its outer layers in a series of gentle exhalations. Finally, the star will eject its outer envelope entirely, creating a planetary nebula, a glowing shell of gas expanding into space. At the center will remain the core, a white dwarf, a dense stellar remnant about the size of Earth, but with about half the Sun's mass. Kepler 56d will still be there, orbiting the white dwarf, a lone planet in a system that once held multiple worlds. The white dwarf will cool over billions of years, gradually fading until it becomes a black dwarf, a cold, dark stellar remnant emitting no light. This will take trillions of years, longer than the current age of the universe. For now, white dwarfs simply cool and fade, dim embers in the darkness. and Kepler 56d will orbit on through the eons, a silent witness to the death and transformation of its star. Universality to these processes. What happens to Kepler 56 will happen to countless other systems. What happened to our solar system's formation, the coalescence of planets from a disk, the migration and scattering and settling into stable orbits, is mirrored in Kepler 56's history. Stars and planets obey the same laws of physics everywhere in the universe. Gravity works the same way. Nuclear fusion follows the same rules. Tidal forces have the same effects. The particular details vary. Each star has a slightly different mass, a different composition, a different rotation rate. Each planetary system has a different number of planets, different masses, different orbital configurations. But the underlying processes are universal. This is one of the great insights of astrophysics. The universe is comprehensible. We can study distant stars and planets and understand them using the same physics we test in laboratories on Earth. We can predict their futures and reconstruct their pasts. We can see in Kepler 56's rapid rotation the fingerprint of a consumed planet, and we can understand why that planet's infall would spin up the star. Science connects us to the cosmos. It shows us that we are part of something vast, that the atoms in our bodies were forged in stars, that the same forces that shape galaxies also shape our lives. There is beauty in that connection, a sense of belonging to the universe, of being made of star stuff, as Carl Sagan famously said. Question of what happens to a star after it consumes a planet. Does it affect the star's subsequent evolution? The answer is complex and depends on the planet's mass and the timing of the engulfment. If a star consumes a planet early in its red giant phase, when the star's envelope is still relatively compact, the planet's material may reach deep enough into the star to affect the core. This could potentially alter the star's subsequent evolution, changing the timing of helium ignition or affecting the star's luminosity. If a star consumes a planet later, when the envelope is already very extended, the planet's material will be diluted throughout a large volume. The effect on the star's structure will be minimal. The most noticeable effect might be the change in surface composition, the temporary enrichment in the heavy elements, which would fade as convection mixes the material throughout the envelope. The rapid rotation caused by the planet's angular momentum is more long-lasting. The envelope can remain spinning rapidly for millions of years after the engulfment. This rotation can affect the star's magnetic field, potentially leading to enhanced stellar activity, such as star spots or flares, though this is speculative. Over time, the rapid rotation will slow. Magnetic braking, the loss of angular momentum through a magnetized stellar wind, will gradually spin down the star. Tidal interactions with remaining planets might also play a role. Eventually, the star's rotation will settle back to a slow rate typical of red giants. But for now, Kepler 56's rapid rotation stands as evidence of its dramatic past, a signature visible to anyone with the tools to measure stellar oscillations. Attention to the third planet, Kepler 56d, the massive world that orbits far enough from the star to survive. This planet is fascinating in its own right. With 5.6 times Jupiter's mass, It is one of the most massive planets known. It straddles the boundary between planets and brown dwarfs. Brown dwarfs are objects that are more massive than planets, but less massive than stars. They form like stars through the collapse of a cloud of gas, but they do not have enough mass to sustain hydrogen fusion in their cores. The dividing line is around 13 Jupiter masses. Objects more massive than this can fuse deuterium, a heavy isotope of hydrogen, in their cores, but they cannot sustain regular hydrogen fusion, which requires temperatures and pressures that only more massive objects can achieve. Kepler 56d, at 5.6 Jupiter masses, is well below this limit. It is definitely a planet, but it is still very massive. Such massive planets are relatively rare. Most known exoplanets have masses below a few Jupiter masses. Planets with masses between 5 and 10 Jupiter masses are uncommon, perhaps because planets this massive tend to accrete enough material to push them over the brown dwarf threshold. Or perhaps planets this massive are difficult to detect. Radial velocity surveys are more sensitive to massive planets, so we might expect to find many of them. But if massive planets tend to have wide orbits, taking many years to complete one orbit, then they are harder to detect because the radial velocity signal takes longer to observe. Kepler 56d orbits every 2.7 years, which is on the borderline of what is detectable with reasonable observing campaigns. The fact that it was detected at all is a testament to the persistence and skill of the observers. This planet's gravitational influence on the inner system is substantial. Its mass and orbital configuration suggest it played a role in shaping the system's architecture, perhaps scattering other planets, perhaps tilting the inner planet's orbits through gravitational perturbations. When Kepler 56 becomes a white dwarf, Kepler 56d will continue to orbit. The white dwarf will have about half the Sun's mass, so the planet's orbit will be somewhat altered by the reduction in the star's mass. When a star loses mass, the gravitational pull weakens and planets' orbits expand slightly. But Kepler 56d will remain bound to the white dwarf, a permanent companion. White dwarfs are fascinating objects. They are incredibly dense. A white dwarf with the Sun's mass compressed into the volume of Earth has a density of about 1,000,000 grams per cubic centimeter. A teaspoon of white dwarf material would weigh several tons on Earth. White dwarfs are supported against gravitational collapse not by thermal pressure, as normal stars are, but by electron degeneracy pressure, a quantum mechanical effect. Electrons in the white dwarf are packed so tightly that they resist being compressed further, not because they are hot, but because quantum mechanics forbids two electrons from occupying the same quantum state. This creates a pressure that holds the white dwarf up. White dwarfs have no internal energy source. They do not fuse elements. They simply cool, radiating away their residual heat over billions of years. A newly formed white dwarf might have a surface temperature of 100,000 Kelvin, glowing blue-white. Over billions of years, it cools to 10,000 Kelvin, then a few thousand Kelvin, eventually becoming a dim red ember, and finally, a black dwarf, too cool to emit visible light. Kepler 56d will orbit this white dwarf, bathed in the dwarf's dim light. The planet will be cold, far from the white dwarf, receiving little warmth. If it has any atmosphere, that atmosphere will be frozen, condensed onto the planet's surface as ice. The planet will be a dark, silent world, circling a dying star in the emptiness of space. In endings, there is beauty in the cycles of birth and death that govern the cosmos. Stars are born from the remnants of previous stars. Planets form from the debris of stellar explosions. Life, on Earth at least, arose from the chemistry of carbon and water, elements forged in stars. And when stars die, they return their material to the interstellar medium, enriching it, seeding it with heavy elements, preparing it for the next generation of stars and planets. Kepler 56's story is part of this grand cycle. The star was born from a cloud enriched by previous stars. It has lived for billions of years. It will die gently, ejecting its outer layers into space. Those layers will enrich the surrounding gas, contributing heavy elements to future stars. The carbon and oxygen synthesized in Kepler 56's core will someday be incorporated into new planets, perhaps even into living organisms if life arises on those worlds. The matter that made up Kepler 56's planets, including the hypothetical consumed planet, will also be returned to space. When the star becomes a planetary nebula, the atoms from the planets will be mixed with the stellar material, indistinguishable, scattered into the cosmos. Nothing is truly lost. Matter is conserved. Energy is conserved. The universe recycles everything. Stars are temporary structures, stable configurations of matter that exist for a while and then transform into something else. Planets, too, are temporary. They form, they exist. They are sometimes destroyed, and their atoms go on to become part of something new. This is the nature of the cosmos: impermanence and transformation. Change is the only constant. But the laws of physics, the relationships between matter and energy, space and time, remain constant. The same equations that describe Kepler 56's evolution describe our sun's eventual fate. The same forces that will consume Kepler 56b are forces we can measure and understand. In the darkness, let your mind wander among the stars. Picture Kepler 56, glowing orange-red, a swollen giant 3,000 light-years away. Picture its planets, silently orbiting, traced by gravity and time. Picture the massive outer world, Kepler 56d, keeping its distant watch. Picture the star's interior, the core and envelope spinning at different rates, misaligned, a memory of a planet that fell into the star long ago. Think about the light that left that star 3,000 years ago. Light that is reaching Earth now. Light that astronomers collect with telescopes and study with instruments. Light that tells the story of a distant star and its doomed planets. Think about the vastness of space, the 3,000 light years between us and Kepler 56, the billions of stars in our galaxy, the billions of galaxies in the observable universe, each containing billions of stars, many with planets, many with stories as complex and beautiful as Kepler 56's story. Think about time, the billions of years of cosmic history, the slow evolution of stars, the patient orbits of planets, the long, slow processes that shape the universe. There is no hurry in the cosmos. Stars live for billions of years. Planets orbit for billions of years. Changes happen slowly, gently, inexorably. And yet, from our perspective, brief as it is, we can glimpse these vast timescales. We can measure oscillations that take hours. We can predict events 100 million years in the future. We can reconstruct histories billions of years old. This is the power of understanding, the gift that science gives us, the ability to see beyond our immediate experience into the deep structure of reality. 6 is a reminder that the universe is both beautiful and indifferent. It does not care about individual stars or planets. It follows laws, simple mathematical relationships, and those relationships play out in complex and sometimes dramatic ways. A star expands and consumes its planets not because it is malevolent, but because that is what stars do when they exhaust their fuel. A planet's orbit decays not because of any intention, but because tidal forces dissipate orbital energy. And yet, we can find meaning in these processes. We can see in Kepler 56's story a reflection of our own mortality, the knowledge that all things end, that our sun will someday swell into a red giant and render Earth uninhabitable. The stars and planets are temporary. But we can also see the beauty in the process, the transformation, the recycling of matter, the continuity of the cosmos. Every ending is a beginning. When Kepler 56 ejects its outer layers as a planetary nebula, that gas will enrich the interstellar medium. Eventually, it will be incorporated into a new molecular cloud, which will collapse to form new stars. Those stars will have planets. Some of those planets might harbor life that will exist because Kepler 56 lived and died and returned its enriched material to the galaxy. This is the great cycle. Stars give life to planets through their warmth. Stars give heavy elements to the universe through their deaths. And the universe continues, evolving, changing, creating new structures, new possibilities. Slow. Let the tension in your muscles release. You are lying in darkness, but in your mind's eye, you are among the stars. You are drifting through the Milky Way, past nebulae glowing with the light of newborn stars, past ancient red giants slowly pulsating, past dense clusters of stars wheeling through the galactic night. You pass Kepler 56. You see the orange giant star, 4 times the size of the Sun, glowing with patient fire. You see the 2 inner planets, tiny dots against the vastness of space, tracing their orbits. You see the massive outer planet, Kepler 56d, farther out, a giant sentinel. You float in the silence of space. There is no sound, only light, only the faint whisper of radiation, photons streaming outward from the star, carrying energy, carrying information. You are a mote, infinitesimal, in the vastness of the cosmos. And yet, you are also a part of it. The atoms in your body were forged in stars. The oxygen you breathe was created in massive stars that exploded billions of years ago. The calcium in your bones was synthesized in stellar furnaces. You are made of the cosmos. You are the universe becoming aware of itself. In this knowledge, we are not separate from the universe. We are part of the great tapestry of matter and energy, space and time. When we study stars like Kepler 56, we are studying our origins, our history, our ultimate fate. We are looking back at the processes that created the elements we are made of, and forward to the processes that will reshape the cosmos in the distant future. And in this moment, now, as you rest, as your mind drifts, you are connected to it all, to the distant red giant, to the doomed planets, to the invisible forces of gravity and time that shape their orbits, to the light traveling across 3,000 light years to reach Earth, to the scientists who study that light and decode its secrets, to the universe itself, vast and ancient and beautiful. Let the quiet settle around you. Let the weight of the day fall away. You are here, now, in this moment, and somewhere, 3,000 light years away, Kepler 56 continues its slow transformation, continues its patient dance with its planets, continues its journey through the cosmos. The universe does not hurry. It unfolds at its own pace, majestic and serene. The stars will still be there in the morning. Kepler 56 will still be glowing in Cygnus. The universe will continue. But for now, in this gentle darkness, let yourself drift towards sleep. Carry with you the image of Kepler 56, the orange giant glowing softly in the darkness, its planets orbiting, its rapid spin a memory of a world long gone. Carry with you the knowledge that the universe is vast and ancient and still unfolding, still creating, still transforming. All things change, all things transform, and you too are part of this great transformation. The atoms in your body have been recycled countless times since the universe began. They were once part of ancient stars. They were scattered into space in supernova explosions. They coalesced into molecular clouds. They formed our sun and earth. They became part of living organisms. They became you. This is the great truth that Kepler 56 teaches us. The universe continues, ever-changing, never-ending. Let the quiet wrap around you like a soft blanket. Sleep well. The cosmos awaits your return whenever you are ready to explore it again. Good night.